video, I'll be going over a general solution technique for piston cylinder spring type problems. In these types of problems, we've got a pretty general setup that you usually encounter with a outer cylinder that's shown in black here, which is fitted with a spring that spans the entire diameter of the cylinder, such that the contents below the spring are sealed inside and there's no leakage or mass transfer out of the system. Though it's not unheard of to have problems where you may have an inlet or an outlet from this working fluid section of the assembly, where we may have a filling or an expulsion process, but those processes aren't covered in this video. Fitted mechanically to the piston, above it in the upper compartment is a spring whose characteristics will either be defined for you or you may have to infer from some given information in the problem. And to make the problem even more generic here, I've included an orifice, an opening, or a vent, which allows ambient fluid to fill this upper chamber and impress upon the piston whatever pressure it may be at. Also, we can include heat transfer if the problem calls for it. If it's insulated, obviously this quantity would be 0, but for the following analysis and mathematical formulation, I'll include the heat transfer aspect into the problem just to make it as generic as possible. So before we move on to the possible thermodynamic processes and how we would constrain them by defining intermediate or final states, let's list some of the potential variables we would encounter in the problem and further on in the mathematical formulation. So first we could have the ambient pressure given to us, so the pressure value exerted by the ambient fluid in this upper cavity or volume on top of the spring, on top of the piston. And this would work in tandem with the spring and the weight of the piston to impress a pressure upon the working fluid. Also, we may be given or have to derive the piston cylinder cross-sectional area, and I've listed over here as A CYL. We may also be given the piston weight, W piston, which, as I mentioned previously, if we're in a gravitational field and say the gravity is acting downwards in this direction, then this piston is going to experience a force. The force is going to be transmitted through the fluid, and if we divide that force by the wetted cross-sectional area of the piston cylinder, so it's the same as this area that the piston is fitted in and the area of the piston itself, so that F over A is going to give us a gravitational pressure imposed on the fluid. Also, we want to know something or be given something about the initial state of our working fluid. I've listed over here several intensive properties, so pressure and a specific volume may be given, pressure and temperature may be given. I'm also listing quality just in case we find ourselves in a two-phase situation, liquid vapor. There's another variable that I've defined on my own here, a capital X, which I've defined as the distance from this bottom datum line to the equilibrium position of the piston itself in this arrangement. And so the way I've drawn this diagram is that the spring is neither compressed or being flexed or in tension. So its net force is 0, the way I've drawn this diagram, and that's going to be related to the way that these other distances are defined. So down below, the initial spring state is going to be related to this distance y. Let's imagine that this wall thickness up here and down here, as well as the piston thickness itself, are negligible. So this top distance down to where the piston is, defined as y, will just be the equilibrium distance of the spring. So before it's been compressed or strained in tension. And again, capital X is just measured from the bottom of the cylinder to the piston itself. As far as spring properties go, we need to be told or infer from some information in the problem whether the spring is linear or not. So most of the time it's going to be a linear spring, meaning that the force delivered as a reaction to moving the spring is proportional to the distance that the spring moves away from its equilibrium distance. So again, at a distance y in this problem, the spring is neither in compression or in tension, so it's not giving a reaction force. But if we say move away from this equilibrium point, minus delta. So delta I've defined to be 0 in this equilibrium plane here. But if we move upwards, the spring is going to be compressed and then give us a reaction force downwards. Whereas if we pull downwards and have a positive delta, then the spring is going to be in tension and give us a reaction force that's upwards. And so in order to relate the distance delta to the force we are going to be experienced, or the working fluid will experience by the spring, we need to know, is it linear or not? Now if it is linear, then all we need is one proportionality constant in order to determine the force exerted by the spring and relate that to the distance it's moved. Now if it's not linear, then we may need a series of constants, and that's why I've listed k sub n here. There could be, say, an nth order type of spring where we need a polynomial in terms of the delta, the distance it's moved from equilibrium, in order to determine the force that the spring exerts. Say, so if we have a nonlinear spring of second order, we may need a K1 constant, a proportionality constant, to be proportional with the delta, the distance moved, to the first power, and then a K2 constant that tells us the proportionality to a distance to the second power, and possibly even a K0 as being just a constant sitting by itself. And finally, with this information here, we should be able to come up with some general expression to relate what happens if we do something to this substance to take it from this initial state to either a final state or an intermediate state or number of states. So we need to be given some information about the thermodynamic process through which the system goes before we really can move further in the analysis. To give an example of one type of process, it could be just simply heat addition until we reach a predetermined final temperature or final volume. Therefore, with one more piece of information, we can constrain the end state of the problem and proceed to doing a mass conservation analysis or energy conservation analysis. Regardless of the thermodynamic process or the end state constraints, we can still go ahead and apply mass conservation and energy conservation to get our mathematical analysis started. Up top here, I've simply assumed that we have a closed system. Therefore, the initial mass is equal to the final mass, regardless, again, of the thermodynamic process. In terms of energy conservation, I'm starting with the differential form of the first law for a closed system. So a differential change in internal energy is equal to a infinitesimal amount of heat added to or subtracted from the system, plus a infinitesimal amount of work added to or subtracted from the system. Given this configuration here, the only type of work that we'll have to deal with is boundary work or pressure work. And I've inserted our definition for boundary work right here, so minus PdV in terms of the work. Q I've left the same for du. A lot of times what they'll do is they'll ask you to solve for the heat transfer after they've constrained the thermodynamic process and the end state or intermediate state. So what I've done is rearranged my expression for the first law in terms of Q. Okay? And then I've done nothing more than integrated between the initial state and the final state. And if there's more than one state in the problem, you can actually perform this integration sequentially. Say, if there's 3 states, we can go from 1 to 2, and then from 2 to 3. And these integrals are actually additive. So if I wanted to integrate from 1 to 3, I could actually just sum 2 integrals between 1 and 2, and then from 2 to 3. So this analysis still applies. But going back from just 1 to 2, the integral of del Q from 1 to 2 is equal to, what I've done is taken the mass out of both of these expressions here. So realize that this capital V is the total volume of the working fluid, not the specific volume, and this capital U is the total internal energy of the working fluid, not the specific internal energy. Therefore, in both terms, I can actually extract the mass, because it's constant throughout the process, and pull it out front here. And so what we have left over is m times the quantity, the differential change in internal energy, plus the pressure of the working fluid, times a differential change in the specific volume of the working fluid, and this entire expression is integrated from state 1 to 2. In order to find out, or actually integrate this del Q, we would need to know something about the thermodynamic process, but we can actually just absorb that all into this bulk Q12 term and actually not do any specific integration. So really, it's just adding up differential amounts of heat that were added or subtracted to the system between states 1 and 2, and we can call that bulk term just the total heat transfer or the net heat transfer to the system or from the system between states 1 and 2. And this is equivalent to, I've just pulled the mass out front. du is an exact differential, so integrating du, I just have u2 minus u1, the internal energy at state 2 minus the internal energy at state 1. And then plus, I've kept this second term inside of an integral, because that's really where most of the analysis for piston cylinder spring problems comes into play. So I've got the integral from 1 to 2 of a function. I didn't make it explicit up here, but P is a function. The pressure is a function of the specific volume times dV. And so really, if you look at it again, this entire integral right here times the mass represents the total amount of boundary work absorbed or given up by the working fluid during said thermodynamic process. And it's going to be this term that is going to be the focus of the remainder of the analysis for this type of generic problem. With our result from the first law, or energy conservation, we get this equation up here for the total amount of heat transfer during the process going from state 1 to 2. And really the term that we're concerned with right now is the total amount of work transfer, or specific work transfer. That's this integral right here. When multiplied, that's the total work transfer. But let's see if we can expand this expression here in terms of more readily known information, or more fundamental information. So I need to know what this function P of V is before I can integrate it with respect to V. And I've written out an expression for P of V, which really is derived from considering all of the forces that are acting on the working fluid. Now if we go back to our diagram here, and this is a bit of a recap from the initial problem statement. Here's the working fluid in the bottom chamber, and we've got three different forces that are acting on this fluid. We've got a gravitational force that is being transmitted as a body force to the piston itself, and the piston is supported by the working fluid. This force, if we divide it by the wetted area or cross-sectional area of the cylinder, we get a gravitational pressure that's applied. And this is actually the second term in this expression. So the weight of the piston, the gravitational force, divided by the area of the working fluid that's supporting it is going to give us a gravitational pressure. I also said that this particular assembly is vented to ambient conditions. So ambient fluid is actually allowed, the gas is allowed to fill this chamber, and whatever ambient pressure may be is also impressing itself on the working fluid. So I've included that pressure here as well. And there's only one more term, and that's associated with the spring and the spring's force. I've made the assumption that the spring is a conventional linear spring, so the magnitude of its force is directly proportional to its deflection from equilibrium, or its equilibrium length. So any deviation from y. And so I've inserted here minus k delta as the spring force, and then normalize that or divide it by the cylindrical cross-sectional area of the assembly in order to get a spring pressure, or effective spring pressure. And it makes sense, the minus sign here, if delta is positive, then the spring will be in tension and pulling back, and it's actually relieving, okay, some of the pressure that would be experienced by the working fluid. Otherwise, if delta was negative, okay, then this term would be positive, and the spring would actually be transmitting a force through the piston to the working fluid, rising its pressure. Now there's going to be a balance between the volume change and the forces, and that's going to be more clear as we expand this expression in terms of volume. So if we look at an equation for the working fluid, the volume that it takes up, it's simply the cross-sectional area of the cylinder, now times this expression here. So initially when delta is 0, the fluid takes up just a cross-sectional area times capital X. But imagine if there's a deflection from equilibrium. If delta is positive, then the volume that the working fluid takes up is going to be smaller, and hence if I plug in a positive delta here, this term becomes smaller, and consequently the working fluid's total volume is smaller. Okay, so this minus delta accounts for the fact that there's going to be fluctuations away from the equilibrium distance x. Okay, we can convert this total volume into a specific volume simply by dividing by the working fluid's mass, which we may need to determine by other means, given some kind of initial condition in the problem, or maybe it's given in the problem statement. Finally, if we can manipulate this expression for the volume or specific volume of the working fluid and solve for the variable delta, or the deviation from equilibrium of the spring, we can get a more generic expression and finally arrive at the expression for pressure we want in terms of the specific volume of the working fluid. So again, rearranging this expression and plugging in, we get the same first two terms. So we've got the ambient pressure and the gravitational pressure. But this third term actually is expanded into two terms. And it's a linear function, so if we were to ignore these and just consider the spring pressure equation, we've got a term right here where we've got our slope multiplied by the specific volume, and then this is our intercept as well. With an expression for the pressure of the working fluid as a function of its specific volume in hand, I can simply insert this expression into my rearranged form of the energy equation and perform the integration first before plugging in the final numerical values to get a result for the total heat transfer. So if I perform this integration, I'll come over here, and this integral again represents the specific work addition to or from or by the working fluid from states 1 to 2. And simply the integral of P of little v, the specific volume, d little v, d specific volume. So just plugging in my expression for P of v, I've got P ambient plus the weight of the piston divided by the cross-sectional area of the cylinder, minus the spring constant times the equilibrium distance of the piston from the bottom of the spring, capital X, divided by the cross-sectional area of the cylinder, plus the expression, the spring constant times the working fluid's mass, divided by the cross-sectional area of the cylinder, times the specific volume of the working fluid, this whole expression multiplied by dV. Something I didn't mention previously, if I neglect these two terms here, the ambient pressure and the gravitational pressure exerted on the fluid, and just considered these two terms associated with the spring, if I set the volume, or the specific volume to 0, or m times v, which is the total volume, if I set it to 0, this term goes away and I just get a negative term, which would imply a negative pressure. And let me explain what this means. So the way I had drawn the diagram before, if v goes to 0, then x would go down to 0, and the piston would be sitting at the bottom of the cylinder. And the spring would be in quite a bit of tension, so it's pulling up. And actually the graph would look similar to this, which I'll explain in a minute, but instead of having a positive intercept, it's going to have a negative intercept, and it would just mean that since there's no other pressures acting on the fluid as x tends to 0, the spring is the only thing that's going to be pulling up on the fluid, and it's going to act as a negative pressure. So it's going to seem like a vacuum pressure to the fluid inside. But that's not the case when we've accounted for both the weight and the ambient pressure adding to the spring's imposed force. So integrating this expression with respect to specific volume, we can take the constant terms here, group them together, integrate them with respect to dV, and so we just get a V2, or little v2 minus little v1 over here, and plus the expression Km over A times the integral of V dV, which gives us, evaluated at the end states, V2 squared over 2 minus V1 squared over 2. Now, if we had complete information about the thermodynamic initial state and end state, and all of this mechanical information about the spring and the piston and the ambient fluid and the geometry, this would be the end point of the problem. We could take this expression, insert it back up here in place of the integral, and go ahead with our internal energy information and specific volume information, plug everything in, and get a numerical value for heat transfer. But in a lot of problems, they won't give you any mechanical information about the spring or the size of the piston, if there is any ambient pressure or not. And so what we need to do is neglect some of these mechanical quantities and see if we can come up with an expression for P of V in terms of purely thermodynamic information. Okay, so I've drawn a graph over here, and what I want to do is attempt to get both the slope, which is Km over A, and this intercept term, P plus the gravitational pressure, minus this vacuum pressure term based on if the spring were fully extended. I want to get all of these in terms of pure in-state information or pure thermodynamic quantities. Okay, so I'm going to have an intercept and a slope. The slope, dP dV, again, is just what's being multiplied by the V in this expression here. Okay, so Km over A. But just back from algebra, you know that if I have 2 points, if I am given information about the initial thermodynamic state and the final thermodynamic state and can fix them, I should be able to find pressures and specific volumes at those 2 points. And if I take a difference, say P2 minus P1 divided by V2 over minus V1, that quantity will be equivalent to Km over A. And I can replace that in this expression here. So 1 down, 1 to go. So these 3 terms add up to my intercept. So when the volume tends towards 0 or goes to 0 mathematically, I'll have a positive pressure intercept. And I need to get an expression for the value of pressure here when the specific volume is 0. And back from algebra, you can utilize what's called point-slope form. And this is nothing more than a rearrangement of this slope equation on the right-hand side. So if I know one point and I know the slope of the line, I should be able to calculate another point on the line, especially when I can set one of the values, so the V value, to 0. So if I say P at volume is 0 minus P star, and P star could be any other pressure on this line. So it could be P1 or P2 if known. And that's equal to this dP dV term, or the slope of the line, times V at 0, V equals 0, so this term will go to 0, minus V star. And so V star is going to be the corresponding specific volume to the state corresponding to P star. And so, as written over here, P star can be either P1 or P2, and V star can either be V1 or V2. They just need to be consistent as a pair. So P1 and V1 go together, P2 and V2 go together. So setting V sub 0 to 0 and rearranging, we get that the pressure as the specific volume tends to 0, or is 0, is equal to this, P star minus dP dV times V star. And plugging in our expression over here for dP dV, we get P at the specific volume is equal to 0, or our intercept, pressure intercept, is equal to P star minus the quantity P2 minus P1 divided by V2 minus V1 times V star. Now with both of these quantities known in terms of purely thermodynamic in-state information, I can go on to plug them back into my P of V equation, perform the integration, and then simplify to get an expression that will work if only thermodynamic information is known. Now with an expression for pressure as a function of specific volume in terms of purely thermodynamic information, as written here in blue, we can actually perform the same integration to solve for the work done on or by the fluid from state 1 to 2 and see what we get. So again, the work from 1 to 2 is the integral from 1 to 2 of this function P of V, little v, dV, and this plugging in our new expression for P of V and integrating, we get a constant term times the integral of dV, which is simply V2 minus V1, plus this constant slope term we can pull out times the integral of V dV, which gives us a term out here of V2 squared over 2 minus V1 squared over 2. At this point, all we need to do is algebraic simplification. If we go down to the next line, I've simply multiplied this expression through, and we get 4 resulting terms. And the second expression here, I've factored out the 1/2, and then I factored the difference of squares into this product, V2 minus V1 times V2 plus V1. So further algebraic simplification from this point leads us to an expression for the specific work done by or on the fluid from 1 to 2 as 1/2 times the quantity P1 plus P2 times the quantity little v2 minus little v1. Now if we plug this result back into our manipulated form of the energy equation, or the first law, we can get a closed form expression for the heat transfer to or by the system to the surroundings from state 1 to 2 as equal to the mass of the working fluid times the entire quantity, the difference in the specific internal energies from state 2 and 1, plus 1/2 the quantity P1 plus P2, quantity V2 minus V1, with the second term representing the work transfer done in the process from going to 1 to 2 in the piston cylinder spring assembly.
The Teaching Center, UF's Learning Resource Center.